Hello, my name is Jason Nguyen, and my GIS project is on transportation. Now, here are the libraries that you are going to need before you look at my code, and that's the SF, dplyr, svdata large, svplanner, and tmp. Now, introduction. This project will talk about transportation. What is transportation, you ask? It's a way to transfer continuously in geographic space between point A and point B. And the topics that we will come across is aerial units, which are main modes of traveling, car, bike, and foot in a specific area, and also it does aggregates the average distance of trips made by people living in a particular zone. Next is the desired line that it shows the data of how many people travel in a geographic area. Next is route. So these are lines representing a path along the route network along the desired lines defined in the previous bullet point. And nodes is a way of representing common origin and destinations and public transportation such as bus stops and rail stations. And lastly, route networks represents the system of roads, paths, and other linear features in the area. Now, the case study this project is going to be taking part of is the city of Bristol, located in England. All the topics mentioned in the previous slide will be presented in a case study on this particular area. And here's a few things to know. Bristol is the 10th largest city council in England with a population of 1 million people. With a huge number of population, Bristol is well served by rail and road links and has a very high level of active travel. 19% of citizens ride on the bikes, and 88% walk at least once per month. So taking that into interest, there is an unfortunate problem, and it contains a major congestion problem. So that's why stated above that increasing the proportion of trips made by cycling is the solution. So as you see, the ones in green are color coded for cycles. The red and black are public, and then the blue are representing the borderlines of the city itself, Bristol. Yeah. Area units. So 1 or 2 zones are stored in Bristol zones, and when you see these underscores, they're coming from a database pulled from a document that should be inside my code itself. So a thing to note is that the zones are getting smaller and more dense in more dense population areas. But with this code alone, it won't contain any attribute data on transport. So then therefore leaving only the name and code of each zone. So as you see here, that's what's stated. To add the missing data, we would need to execute a join task. So we're going to take the Bristol OD, and Bristol OD is a origin destination dataset on travel between zones within Bristol itself. So then, as you see, the first column is the ID of the zone of origins, and then the second is the zone of destination. So in the previous coding block, it shows that it has 10 more than 10 OD pairs for each zone, which leads to the problem where we need to cluster the data before it is joined with the Bristol underscore zones. So then that's the coding below to cluster the data. And then now we are grouping the data by zone of origin O. Then you doing that aggregates the variable in the Bristol OD to find the total amount of people living in the zone. Then it is renamed the group O to geocode, so it matches the ID column in Bristol underscore zones object. So right here. Zones at ATTR represents zones in a ID variable, so it can match those in the zones dataset using this function. The results showed that all 1 or 2 zones are presented, and the zones ATTR is in a form that can be joined into the zones. The following code below shows zone ATTR is combining with the zones due to using the joining function left join. So this should be familiar to you guys. Then ultimately, the results is zone of joins, which contains a new column representing the total number of trips. So these are the new columns, total amount of trips in the zone, in each zone in the area. Now, same way that we talked about the origin destination zone, or it could be thought as the same way for destination zones. When you aggregate the zone of origin, you could also aggregate to provide information about destination zone. So the volume code below shows the result zones OD, which contains a new column holding the number of trip destinations by any mode. So as you see here, there are from the left is the commute trips. The right shows these zones of destination, and it is both color coded as you see. Now, unlike zones, desired lines connect the centroid of the origin and the destination zone. In other words, it represents where people desire to go between the zones. So at this point, we already loaded the data due to the other sections, so we're going to be using the same dataset, Bristol OD. So to get the origin destination frame object, which is, in other words, that represents the number of people traveling in between the zones, we have to arrange the OD data by all trips and filter out only the top 5. See here, I provided the code and a physical or a virtual look on what it looks like. Then the next step to do is to calculate the percentage of each desired line that is made by the active modes. So then here's the following code for that. After calculating, there are 2 important things to know, is the differences between the interzonal and intrazonal for desired lines. So the interzonal represents the travel between zones in which the destination end, is different from the origin. Meanwhile, intrazonal represents travel within the same zone. So then here's the following code to differentiate what's the difference. The next step is to convert the intrazonal OD pairs into a SF object to represent desired lines, so it could be plotted on a map with the ST planar function OD2 line, which is right here. With all these codes combined, it should look up to something like this, and this should take a familiar form of the Bristol region itself. As see here, it takes like a rough sketch of what it looks like. The number of trips, as you see, it's very abstract. So yeah. Now going on to routes. So routes are similar to the desired lines, but they can handle more than desired lines. So desired lines are built for straight roads, but they can't really do much. They can't record data when the roads are turning left, or if the roads are being curved, or with full twists and turns. Meaning routes are more complex, meaning it's more beneficial for those type of situations. So then the routing is done in the code chunk below by the ST planar route, which is down at the bottom here. In the code above, ST length determines the length of a line strings, and falls into the distance relation category. That's just taking record of how long the road twists and turns. And then we apply a simple filter operations before letting the OSRM service do the routing on the server. Then from this point on, we can keep the new route that was separated from the straight line to represent the same trip, or we can combine it together, which is these following lines of coding, which leads up to this picture. Now nodes in geographic transport data are zero-dimensional features, And there are two types of them. One, they are not related to network, and two, they are related. Then the first stage to identify the desired lines with most public transportation travel. To make this approach easier, we will select only the top 3 desired lines, which is this following code. Now the next step is to break those up into 3 pieces. This can be done by converting a desired line into a multi-line object consistent of 3 line geometries representing origin, public, and transport and destination. Just right here. Now, as explained, the initial desired rail lines now have 3 additional geometry lists. Columns representing from home to origin, from there to the destination, finally from destination station to destination. Now, route networks is the last one. So to avoid having to request the data form OSM repeatedly, the code below used the Bristol _ way, which contains point line data for the Bristol area. Now, as you see, the code above contains at least 3,000 segments on the transport network. As previously mentioned, the route networks can be useful by presenting as mathematical graphs with nodes on the network using iGraphs. iGraphs is the name of a library that you can install in your RStudios. But then the problem is that those geographic attributes in iGraphs will be lost. So as a substitution, spatial lines network is the way to go, because it can simultaneously use as a graph and a set of geographic lines, so it covers both ends. And here's the code itself. Spatial line networks on Waze Freeway. Then the output of the previous code wasteland is a composite object that includes the spatial component, graph component, and the weight field. And that is from shown below, from this code that makes this. And yeah. Now, combining this all together, this final section demonstrates the policy of geocomputation for transport applications by identifying locations where new transport infrastructures may be needed. To prove, the final code chunk of this section combines these strands of analysis. It adds the car-depend routes to route car short with a new object route rail, and that creates a new column representing the amount of traveled. So you see, the results of the preceding code are visualized below this paragraph, which shows routes with high levels of car dependencies and high level opportunities for cycling rail stations. And the thing to keep in mind though is that people do not travel to zone centroids or always use the shortest route algorithm for a particular mode. However, these routes demonstrates routes along with cycle paths could be prioritized from car dependencies and public transport perspective. So yeah, you see these roads could be replaced with cycleways and all. So yeah. Now, this project provides a taste of the possibilities of using geocomputational for transport research, and it has explored some key geographic elements that make up a city's transportation using open data and reproducible code. Then these results could help plan where investment is needed. So wherever in the world, this could be used as a possible solution when a problem occurs relating to congestion. So that's it for my presentation. Thank you for listening and have a wonderful night.